Good morning. Time for some more circuits. So I know we've done a lot of circuits so far. I think we've done like 3 classes on just circuits. It's like, what, 2 hours? 2.5 maybe? On just circuits with batteries and resistors. And voltmeters and ammeters. But, you know, those are basically just batteries and resistors anyway. So we're going to do one more time. This will be it. Then we'll move over on to capacitors and solenoids, or maybe inductors, but they're kind of similar and the same. So capacitors and solenoids, LRC. L is for inductor. Okay, focus, back on track. So we have a AP style problem. Oh, thank God. Yep, that's good. And we're going to work through this and see where we go. Get a little bit of practice. So we have a circuit, as shown above, which consists of a source of variable EMF, electromotive force, a battery, and that little arrow right there, that means variable. It's like a dial that you can turn. An ideal ammeter, meaning that it has zero resistance, zero internal resistance. An ideal voltmeter, which means it has maximum, infinite internal resistance, meaning it has zero current flowing through it. So, draw a little arrow right here. Actually, I'll zoom in even more. Little arrow. That's an arrow. Call that, that's terrible. Call that, how did I get the eraser? It's good to know how to do that, but, IV for the voltmeter equals 0. There is no voltage flowing through there. In reality, there's a little bit of voltage, but it's considered negligible. Okay, focus. Back on track. And resistor of resistance R, that guy. And a sample of wire with resistance little r. So this one is assumed to be known. This one is unknown. Though we don't actually know what big R is either. It's a known unknown. That's probably not true. How does the current through the wire sample compare with the current through the resistor R? Okay. So what this is saying is we have the battery creates a differential voltage, and this manifests itself as a current. So we're going to have positive charges flowing in the positive direction, like so. I say positive charges in the positive direction to distinguish it from reality, which is negative charges in negative reality, or negative direction. Negative reality. Okay, so current is going to flow up this way. Some, approximately 0. I could write it as 0 plus, goes through the voltmeter. Goes through big resistor, goes through little r, through the ammeter, and then back to the battery. So all the current that flows through big R is also going to flow through little r. So the two will be the same. How does the current through the wire sample compare with the current through resistor R? It's greater, it is the same through both. Yep, and that's because we have an ideal voltmeter. If we did not have an ideal voltmeter, then that answer would be different. If we did not have an ideal voltmeter, it would probably be more current would flow through little r than big R, because some of the current would be bypassed. How does the potential difference across the wire sample compare with the potential difference across resistor R? Okay, now this is talking about a voltage drop. So I'm going to throw in some random numbers, pseudo-random. I guess everything in life is pseudo-random. That's a much deeper concept than I intended to get into. So I'll say this is a 9-volt battery, which means top here is 9 volts, below is, 0 volts. Then I'll say this is what, 3 ohm? No, let's call it a 2 ohm, and we'll call this a 1 ohm. So then the total current, these are just made up numbers, so don't made up. Delta V over R, so current would be 9 over 3, which we have 2 resistors in series. And so the R equivalent is just them added together. So we have 3 amps. And we'd have a voltage drop across the first one of, let's see, V equals IR. we know that we have 3 amps going through it. So it'd be 3 times 2, which would be 6 volts. 6 volts, which would mean that this one would have to be 3 volts, which would make sense because it'd be 3 amps times 1 ohm. So if we have 2 and 1 here, then we would have 6 volt drop across the first one and 3 volt drop against the second one, assuming we have a 9 volt battery. How does the potential difference across the wire sample compare with the potential difference across the resistor? Okay, so in this case we had 3 volt and a 6 volt drop. Now let's change some of our assumptions. Since they were all made up to start with, it's pretty easy to change. The nice thing about living in a complete fantasy world is you don't have to worry as much about logical consistency. So now let's say that we have them the same. So before we had 2 ohm and 1 ohm, so now I'll have 1 ohm and 1 ohm. So it means that equivalent resistance would be 2. Current would be V divided by R, which would be 9 over 2, which would be 4.5. And so the voltage drop across the top resistor would be V equals IR. Same as I equals V divided by R, we just rearrange the equation. So now we know 4.5 amps. So we have 4.5 times 1, and now we'd have a 4.5 volt drop. And so you'd find the same thing for the other resistor, little r, as well. And so if we had a 1 and 1 ohm resistor, then it'd be 4.5, 4.5. If we had a 2 ohm resistor and a 1 ohm resistor, then it'd be 6 and 3. So the moral of this story is that we're going to start with whatever EMF we have. In this case, I said 9 volt battery. So we're going to start with all of our voltage. In the end, we're going to have none of our voltage. So it's what the resistance and the resistors do is it shows where the biggest drop is going to happen. You could look at it as the ratio of they're basically partitioning out the voltage drop as a ratio. So when we had 2 and 1, this had 2 over 2/3 of the drop here and 1/3 of the drop here. When we had 1 and 1, then we had 1 over 2 of the drop there, 1 over 2 of the drop there. And so even though we know the current through both of them will be the same, regardless of the resistor sizes, because one current comes in, one current comes out. Like you could say that's Kirchhoff's current law, or you could also use the hydraulic analogy and be like, look, this is just water in a pipe. If you start with so much water, you're going to end with so much water. If you don't, then there's some terrible leak in the pipe, or you have compressible water, which, though possible, is assumed not to be possible. So this is going to depends on the resistance of the sample. Yes. So it depends on the resistance of the sample. It also depends on the resistance R. But they don't give us a depends on the resistance R. Boom, boom. Hope that makes sense. Hope I didn't speak too quickly there. But the potential difference across the wire sample will depend on, with the difference across resistance R. Yep. So the voltage drop across each resistor will depend on each specific resistor and how they ratio out together. And if you don't believe me, you can just pick up a whole bunch of random values for the resistance, do a whole bunch of Kirchhoff voltage laws, little loops, and like we just did with the 1 and the 2 and the 1 and the 1, and give yourself a sufficient number of warm fuzzies that is true. With the sample of wire in place, the electromotive force of the source is set to a given value. Okay? The current through and potential difference across the resistance R is measured. Okay, so we have VR. Okay? And we have IR. Okay, now this is interesting. So if you were clever, which I'm sure all of you are, they basically give you the answer to part A in this sentence here. Because if you look here, the current through R is measured even though the ammeter is down here. So what's that telling you is that current through R, little r, and ammeter are all the same. And so the current is the same throughout this circuit. Okay. The current through potential difference across resistance R is measured. This is repeated for several values of electromotive force. Okay. And the data are recorded. It always bothers me that data is plural. Darn you, English. And the data are recorded in the table below. Kind of like media. Okay. Okay, so they didn't actually ask us a question there. They just told us, which is nice of them. All right, then let's look at the second part. Okay, here we go. Indicate below which quantity should be graphed to yield a straight line that can be used to calculate a numerical value for the resistance of the wire sample. So what this is saying is, use to calculate. So we're going to have to graph these here. You may use the remaining columns in the table above as needed to record any quantities that you indicated that are not given. Okay. So they're going to want us on the grid below, plot the straight line data from points, clearly scale, enable all axes, including units if appropriate. Draw a straight line that best represents the data. Okay. So whenever they say something like straight line, graph, linear, I'd recommend writing out your equation for a line. Y equals mx plus b. So for this, we're going to probably want to do Kirchhoff's voltage law. We'll just do a loop, and we'll see if that gives us something kind of this form. So I can say that epsilon minus voltage R minus voltage little r equals 0. And this is Kirchhoff's voltage law. We're given voltage across R, and we're not given VR. So I'm going to take VR and I'm going to change that to V equals IR, which is just a rewriting of I equals V over R, Ohm's law. And so we're going to have epsilon, which is electromotive force, V over R equals IR. Okay, so this is the small resistance, and that is the current through little r. Now the current, as we showed in A, and they told us in B part 2, maybe, this is going to be the same as the current through big R times R. So I just substituted the current through this for the current through that, because they will be the same. And this kind of looks like that. So we're going to have, and we're trying to find a resistance for the sample of the wire. So we're trying to find this. So that'll be our unknown. That'll be X. This will be our Y variable. Yep. I like this. So I'm going to write this out as epsilon minus VR equals IR times R. Now, to do this the more traditional math way, I think that this should be the Y and this should be the X value, because this is the dependent variable and this is the independent variable. But I'm not going to do that because I want to use this equation, straighten slightly. Aha, it worked well. And it doesn't really matter which axis is which, as long as it's consistent. So what I want to say is epsilon minus VR is y. I want to say that R equals that'd have a changing slope, wouldn't it? And I guess if this is the case, I'd probably want to say that I equals M, but M is supposed to be constant. So, and we have a changing current. So maybe I should rewrite this one more time. E minus V over R over IR equals resistance R. Okay, so then you know, I'm going to say that it'll turn out okay, and I'm just going to graph this. I like that better. I don't want to get too crazy with my axes. So I'm going to say that my y-axis is voltage. And horizontal axis is indicated this current should be graphed to yield a straight line that could be used to calculate a numerical resistance for the sample. And the horizontal axis will be current. Yes. On the grid below, plot the straight line data, clearly scale and label all axes, including units if appropriate. Draw a straight line. Okay, so now I'm going to take this. This will be my y-axis. Did I say that? Yes. And this will be my x-axis. I will plot it real quick and then be right back. Okay, so now we have the data graphed. Draw ourselves a straight line. Here we go, something like this. Maybe we can make it thinner. Oh, yes. Ooh, change it to blue. There we go. Let's see, does that look about right? Move this guy over. And maybe a little bit less. There we go. And I know you're not traditionally supposed to draw a line that big, it should stay on the graph. But it works close enough. Okay. Use your straight line to calculate the value of the resistance of the wire sample. Okay, so if we find, whoop, whoop, click, clack. So the resistance will be E minus VR over I. And so we can do the, find the slope of the line. So you can see that this is the slope. This is E, this is I. And so we'll do y2 minus y1 over x2 minus x1. I'm not even going to use the graph. I'm just going to use a couple data points. So up here, I filled in E minus VR. So I'll use the biggest one, which is 0.33 minus the smallest one, which is 0.071 over, and then we'll do 0.687 minus 0.162. And hopefully that'll give us a positive number. All right, so quick memorize, 0.33, 0.071. 0.33 minus 0.071 divided by quantity, 0.687, 0.162, 0.687 minus 0.162, 0.162, okay? And that should give us a number, and that number is 0.49. Actually, I'll go with 0.5. 0.5 ohms. I know it could be a little bit more accurate, and you probably should be more accurate. And on the test, ideally what you're supposed to do is you're supposed to pick a point and relate it to the graph based on the line, and then pick a point based on the line that on the other part of the line. I don't know. I just make sure the line passes through the 2 points you want to use as your for your slope. So the resistance of this piece of wire is 0.5 ohms. Oop. Okay. The wire sample has a length of 3 meters and a radius of 1 times 10 to the negative 3 meters. Calculate the resistivity of the material. Okay. So resistivity, talked about that a few times before. It's not really a core concept in life, but people seem to enjoy it. So resistivity is measured in ohms times meters. And the equation for resistivity, I'll say rho is resistivity. Resistivity is kind of like a resistance per unit length, which would then make you think that, oh, you should divide by meters. Well, that's true, kind of, sort of, but it's based on the geometry as well of your sample. So this would be the resistance of the material, of the sample, times the cross-sectional area of the sample divided by length, which in this case, the cross-sectional area will be pi r squared. So I'm going to write resistance as small r because that's what they've been given. Pi r squared. I'm going to rewrite the little small as r big because I don't want to confuse radius with resistance. I know, human performance trap. Over length. That's okay, you only have to keep this straight in your head for like 10 seconds. Okay, so wire sample length. Okay, so I'm just going to start putting in numbers and see where it goes. Hopefully it leads to my happy place. If not, then meh. Okay, times 10, 1 times 10 to the negative third. I'm just going to write that as times 10 to the negative third. And then square it all over the length, and they give us a length of what, 3? 3. Okay. So this is going to be a little bit shady. So we have 0.5. I'm going to say we have 0.5 times 10 to the negative 6, because right here, times pi over 3, which cancels out and gives us 1. Yeah, that's shady. It's okay, I don't care. And then I'm going to rewrite this as 5 times 10 to the negative 7. Because 0.5 is 5 times 10 to the negative 1. 10 to the negative 1 times 10 to the negative 6 is 10 to the negative 7. And this is ohms times meters, which is the resistivity, which I think is normally represented by rho, which kind of looks like a P, but it's not. It's an R. What do we got here? What do we got here? 5 times 10 to the negative 7th ohms meters. Okay, and that's how I would do that part. And you only have 15 minutes really to do this problem, so even though I'm taking like half an hour, you should try to work quicker. Suppose the ammeter used to collect the data was not ideal. Oh, that's not ideal. Would the actual value of the resistance of the wire sample be greater than, less than, or equal to parts E? Justify your answer. Okay, so what it's saying here is we got our ammeter up here, and it's saying instead of having an ammeter like this, our ammeter actually looks like it would in reality like this. And there's like this imaginary black box here, and that is our internal. Okay, so then come back down here. It's asking, suppose the ammeter used to collect this data was not ideal. Would the actual value of the resistance of the wire sample be greater than, less than, or equal to that part calculated in part E? So I'm going to do it this way. So the concept here is not difficult, but it's easy to get kind of turned around. So I'm going to make 2 columns here. measured and actual. So when you have the ammeter, that's not ideal. We'd have our resistance R like this. Then we have an R internal like this, ammeter, battery, and then another our resistor R up there. And so what we would be measuring would be R plus R internal. What our actual would be R. And you can see here that assuming that Rn is not, the internal resistance is not negative, which I'm not sure if you really can have negative resistance with just a resistor. No, you can't have negative resistance. Okay. So since this value will be actual will be less than measured, we would say that actual would be less than measured. If the ideal voltmeter is replaced by a voltmeter that is not ideal, and the experiment is repeated, would the readings of the ideal ammeter be greater than? Actually, okay. So it's asking about our measured ammeter readings if we have a voltmeter. So I'm going to use the same strategy I did before, except now I'm going to draw another picture, and I'm going to draw something like this. So this is R internal. This is little r. This is our ammeter, which is again ideal. And this is big R. So our measured resistance, which would be V equals I equals V divided by R. Okay. Our measured resistance would have a equivalent resistance, but we'd get more current coming through now, because R equivalent would be, okay, 1 over R equivalent would be 1 over R internal plus 1 over R. And then this would be R plus R internal over R times Rn. Therefore, R equivalent. So we're finding a common denominator, which the common denominator is Rn. So we multiply this by R over R, multiply this by Rn over Rn, and then combine. So R equivalent would be R times R internal over R plus R internal. Okay? So we would measure, so we're looking at the current. With the readings, the ideal, okay, so we're looking at the current. So the current through these two combined would be the same as the current through this resistor, which would be the current through the ammeter. So we can find it at any point. So we want to look at the resistance here. So R equivalent, so R that we would measure with a non-ideal voltmeter would be R times Rn over R plus Rn. And it's hard to see by this, but logically it's probably easier to think through it, that the combined resistance of two resistors in parallel will be less than either one of them alone. So the resistance would actually be less than the actual resistance. And since we would have I'll just say resistance here. So if ideal voltmeter is replaced by a voltmeter that is not ideal, so our measured resistance would be less with a non-ideal voltmeter, and that would allow more current through this section, and that more current allowed through that section would cause more current through the whole thing, and so our total current through the circuit would be greater. Yes. We'd have a greater total current. So if our ideal voltmeter is replaced by a voltmeter that was not ideal, then the ammeter would read the current through the system because the current is the same at each area. This current here at the bottom is not the same as this current at the top, but when they combine, then it'll give us the same current. So the way I would do this second problem is I would draw a picture with your non-ideal voltmeter, and then I would logically think about, okay, so we have two resistors in parallel. Now that we have two resistors in parallel, the combined resistance will be less than either of those resistors alone, and that would then give us a less resistance to flow. Greater flow means more current, and more current to the system means a greater reading on the ammeter. So I know those are really easy to get mixed around. You know it's not going to be equal to. That's pretty straightforward if you intuitively think about it. And then the reason for the first one is resistors in series, and the reason for the second one would be resistors in parallel. And I would probably just draw out something like this in the picture and then say resistors in parallel allow greater flow. Okay, I know this was kind of a in-depth problem. This is kind of the sort of thing you can expect on the AP Physics exam. These questions are no joke. This is a challenging test. I would like to think that I could pass it. I probably could. I'm not, but it's a lot easier to say without taking it. And truth be told, almost anyone can get 100% on this test. The challenge is getting 100% and getting all the questions correct in the time frame that you're given. 15 minutes is moving pretty darn quick for tests. Like 15 minutes for a question like this, that is quite the challenge. Okay, so now we're going to move on to a few multiple choice problems. Now here we have a few multiple choice problems. You have about a minute, a little bit more for each of these, so that's challenging. So you really have to look at it logically, develop a gut instinct, and then go for it. And the more time you can save on one problem, the easier the rest of them will be because I have more time. With that being said, you only need about 60% on this test overall, but the more multiple choice you can get right, the more leeway you can have on the free response. With the free response, you're going to come across a problem you just have no idea how to do, and you don't have time to figure it out. So you're going to lose a lot of points, not because you don't understand the concept, but just because you get sideswiped by something you didn't quite expect. So multiple choice, try and buckle down as much as you can and get as many points as humanly possible on the multiple choice section to kind of give you a leeway on the free response. Most universities, you only need a 5 or a 4. So aim for a low 5 and hopefully you'll get a 4. That is my recommendation. Okay. When two identical resistors are connected in series to a battery, the total dissipated power is P. When the same two resistors are connected in parallel to the same battery, the total power dissipated is. Okay. So I'm going to start by writing out what they said for the first section. So P equals I squared R equivalent. And we know that we have two resistors connected in series. That really bothers me that I did a square bracket there. I squared R plus R, which equals I squared 2R. Okay? And then I'm going to call this power series. Power parallel is I squared R equivalent. Now these are in parallel. So 1 over R equivalent equals 1 over R plus 1 over R, which equals 2 over R, which implies that R equivalent is R over 2, which makes sense. If you have two identical resistors parallel to each other, half the flow will go through one, half the flow will go through the other. pretty reasonable. Okay, so we come back up here. We'll have an I squared R. Nope, I squared R over 2. Yep. And we're trying to look for the relationship between power in series equals some coefficient alpha, proportional. Power parallel, we have I squared 2R equals, and these are the same resistors, right? The same two resistors, okay? Equals I squared R over 2. And we'll leave that alpha in there. I squared cancel. R's cancel. And we're going to get, move that 4 equals alpha. All right, so we know there's a relationship of 4 between the powers. So we can cancel these. We know these aren't it, but maybe this one and maybe that one. So to get the answer, I would logic this out then. If you've heard in life of a short circuit, like you see like in the superhero thingamajiggers, oh no, there's something short-circuited and it overheated and exploded. Well, the reason short circuits are a big deal is because you dissipate more heat. So any of you, like, I don't know if you've carried a bunch of junk in your pocket. I have at various points in my time. And for some reason, at one point, I was carrying like a battery, maybe 2 batteries, and a set of car keys and many other things. And you're walking along, and it's like, wow, my pocket is strangely warm. And it's like, and you start to get worried. It's like, and it's not like uncomfortable, but it's like, there should not be that sort of, what's going on here? And what happened is the battery had battery, some sort of metal, very small resistance between whatever it was, back to each other, and power dissipated was massive. And so the idea that I'm trying to get across here is if you have a low resistance, you'll have more power dissipated. And that might not necessarily be intuitive because you think that, well, power equals I squared R. It's like, well, if you have a low resistance but a high current, do they just cancel each other out? No. The current will dominate in this situation and power will go up. And so what we have here is when the two same resistors are connected in parallel to the same battery, the total power dissipated is more. So when you have the resistors in parallel, the resistance goes down, therefore the power goes up. Also the current goes up. So it's not the first one, it'll actually be the E, echo, for power will be the answer. I know, it took like 3 or 4 minutes to do that. Hopefully you can go, I would do the math and you can skip most of this. So you can be like, okay, 2 resistors in parallel, 2R. 2 resistors in series, 2R. 2 resistors in parallel, R over 2. And then combine them. So this, you could do this problem in about a minute. Okay, next problem. 3 resistors. Sounds like a beginning of a good story. There should be some swashbuckling. Having a resistance of 3 ohms, 6 ohms, and 9 ohms. That actually reminds me more of the Three Musketeers now because, you know, you have a resistance. I think of the French and fighters. French resistance fighters of varying resistance, 3, 6, and 9, are connected in parallel with a 10-volt battery. True statements about the circuit include which of the following? Okay, so I start to panic a little bit because I'm like, wow, that's a lot of information. 3, 6, and 9, how do they compare? So intuitively, I'm going to think that, all right, so I'm not going to think over too much. I'm just going to go over the the questions and see if anything jumps out at me. Because if you overthink these too much and do too much analysis, then you can do 3 or 4 minutes worth of analysis on a question that you don't have 3 or 4 minutes to answer. The current in the 9 ohm resistor is 3 times the current in 3 ohm resistor. Okay, so draw a picture. Resistor, 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 9, 6, 3. And don't need to draw the battery, but I will. Okay, so the current in the 9 ohm resistor is 3 times the current in the 3 ohm resistor. False. The 9 ohm resistor offers more resistance, therefore it's going to have less current, since current equals voltage divided by resistance. The potential difference across each resistor is the same. Yes, that's one of the definitions of parallel. By parallel, you can say that the definition of parallel resistors is parallels that are all at the same resistance or the same voltage difference. That's not a strict definition, but it's a pretty darn good one. Okay, and then the third one, the power dissipated in the 9 ohm resistor is greater than the power dissipated in either of the other 2 resistors. Okay, so false, because for the same reason we talked about in the previous question, as the resistance goes down, the current goes up, and that current going up is what dominates the power dissipation for your I squared R losses. And so your highest resistor is going to have the lowest current, which will provide you with the lowest power dissipated. So this whole greater thing, not true. And so the only one that will be true is B. Yep, that whole 10 volt part, totally useless. Doesn't matter. Lead me astray. Darn you, red herring. God, there was one of the Scooby-Doo shows where they actually had a character named Red Herring, and he'd always lead you astray. When I first watched that show, I was like, I don't know, 10? And I never quite got the pun. But like in hindsight, I'm like, that's really clever. That's a clever character name. Red Herring. Okay. When 2 resistors having resistance R1 and R2 are connected in parallel, the equivalent resistance of the combination is 10 ohms. Which of the following statements are true about this resistance? Okay. Yeah, my visualization is not too good here. So 2 resistors connected in parallel, R1, R2. Okay. So we have R1, R2 connected in parallel. R equivalent 1 over equals 1 over R1 plus 1 over R2. Combine these into a R2 plus R1 over R1 times R2. Do a common denominator and then add these together. Therefore, R equivalent equals R1, R2, or R1 plus R2. Okay? Highlight, move, rotate, and right here is good. Okay. So now we have are connected in parallel. The equivalent resistance of the combination is 10 ohms. Which of the following statements about resistance is true? I probably did a whole bunch of work and didn't need to. Okay, both R1 and R2 are greater than 10 ohms. Okay, so this is just the idea of 2 things in parallel. So we have 2 resistors, R1 and R2. You know, I should have started reading the questions before I got all carried away. Oh, AP type exams, you suckered me in again. Okay, so both, which is true, so only one is probably going to be true. So both R1 and R2 are greater than 10? No. Maybe. Yes. So it's saying that, so if we have a 12 ohm here and a 14 ohm here, when they combine, they probably don't, I just picked random numbers, be equivalent to a 10 ohm resistor, because the resistance of 2 resistors in parallel, when you put them together, the equivalent resistance will be less than either of those alone. Both R1 and R10 are, no. because the equivalent resistor then would equal 5. So if you have two resistors that are the same, their equivalent resistor, when placed in parallel, would be half of which either of them would be. Both are, no. This is, if you have them in series, then their equivalent resistance will rise. The sum of R1 and R2 is 10. This is basically saying the same thing. It's talking about in series. One of the resistances, this is saying, well, we'll just average the resistors. That's not how parallel works. So, question here is I shouldn't have done all that math. All that math I did, wasted time. Be very careful. So, it's probably worthwhile drawing the picture, R1 and R2, just so you have a visual picture of resistors in parallel. But after that, I would not recommend doing all the math that I did. Inefficient use of time. Bush League, amateur. Okay, so that's all I'm going to talk about for circuits using batteries and resistors for now. Next, we're going to move on to conductors and solenoids, which are both, they're exciting. I like them. Specifically, I'm going to talk about LRC circuits involving direct current. We'll talk about alternating current later, but for now, we're going to do just direct current. Appreciate you guys listening. I will see you next time.